So it's a great pleasure to have Professor Joel Moore from University of California, Berkeley today giving this colloquium today. So Professor Moore is a Simon Professor of Physics at the University of California, Berkeley, and a senior faculty scientist at Lawrence Berkeley National Laboratory. His work in theoretical physics studies quantum matter with focus on the remarkable phenomena that emerges as a consequence of entanglement and topology. So he's received his AB in physics from Princeton in 1995, and then actually he spent a year in TIFR, almost a year in TIFR, and then before graduating from MIT. He was a postdoc in Bell Labs before joining Berkeley faculty in 2002. So he's an elected member of National Academy of Sciences, a Simon Investigator and Fellow of American Physical Society. So he has served as a chair in the advisory board of Kavli Institute of Theoretical Physics. And yeah, so it's a great pleasure to have you here. And yeah, floor is yours.
Thank you very much. I'm really happy to be giving this talk in this particular place. You might see why as I go along. But I have to admit, I'd never been here before. I've been to ISC. I've made a few trips to India over the years, but this is definitely the prettiest physics spot I've seen, I think. I should have come earlier. So the point of the talk is going to be that geometric phases turn out to be extremely important in the theory of materials. And without needing a very big background in solid state physics, there's an amazing number of phenomena that you can predict. And it leads you to think about some new things that maybe hadn't been thought about before. So I want to build up to one of the first examples, maybe the first example of a quantized nonlinear response in a solid. But I'll try to maybe motivate it a little bit at the beginning. And please interrupt me. I'll try to keep it to an hour, but I'm happy to spend time answering questions and make the talk part shorter. So by now, we know that the universe has a large number of fundamental particles. But there are a few things that are out there in solids that don't exist as fundamental particles. So I'll talk about one example, which is a Weyl fermion. There are others that, like anyons are another famous example. So there are things that come about, even though they aren't fundamental particles, through this remarkable property of emergence. And the main point of this talk is going to be about unique kinds of responses. So the quantum Hall effect is maybe the first example of a topologically protected response. So far, the only thing I know that it's been good for is redefining units and making like a new standard of voltage and things like that. People talk about other applications that I hope come true. But from a basic science point of view, maybe a remarkable fact about some big solid with defects and thermal fluctuations and so on is that if you ask the right question, it can be perfect again, almost as perfect as one or two particles. So the main I promise I'm not going to give you lectures 2 and 3 today. That's from when I was at ICTS. This talk stops here. So I want to say a little bit as introduction about how there's been about a 40-year process going back to pioneering work of Thouless and collaborators that was part of Thoulless's Nobel Prize of understanding a certain kind of geometry and topology of quantum states and how it matters in solids. And then the new thing I want to build up to, there was a discovery, still fairly recent, around from 2013 to 2015, people found the first example of solids that are topological semimetals. They're kind of like three-dimensional versions of graphene. So now that we have those new materials, what do they do? And I'll talk about what I think is the most interesting they do. It's a kind of chiral photocurrent. But I'll warm up with an example of why, when I say quantization or things like that, you shouldn't take it too seriously in a metallic system. Even though ideal semimetals of various kinds do have some quantization, meaning that something you can measure is easily expressed in terms of fundamental constants, it's never as accurate as it is in insulators. And maybe the simplest example of that is if you want to measure the fine structure of constant of nature, a way to do it is to take a sheet of graphene and hold it up to the light and realize that you can mostly see through graphene. It blocks about 2.3% of the light in the visible, and that 2.3% is pi times 1 over 137, where 1 over 137 is the vacuum fine structure constant. In other words, it's the speed of light that appears, not the speed of the electrons in graphene, which is about 300 times smaller. So you could say that this effect is kind of accidental. It only works because our eyes work at the right frequency. If we looked in the X-ray, it wouldn't work because the bands would no longer be linear of graphene. And if we looked at very low frequency, it would be sort of disorder dominated. But there is a region where some very simple property of graphene, the optical attenuation, is just given, the scale is set by fundamental constants. In fact, you wouldn't expect it to be that good. It's accurate to maybe 1 part in 100, maybe a little bit less, maybe 1 part in 50. You'd expect it to be much worse, maybe 1 part in 2 or something. So I'll come back a little bit later to why there seems to be some kind of cosmic accident that makes it work so well in graphene. So I'm going to talk about both theory and experiment. The theory was done by various people who passed through Berkeley and are now scattered around the world. Fernando is in Spain, Adolfo is in France at Grenoble, Takahiro is in Tokyo, and Dan Parker is at UC San Diego. And there was a collaboration of experimental groups around the world that looked for the effect that I'm going to talk about. But I mostly want to give kind of an introduction to the broad field and why it all really builds on work done here. So the way that we understood, I think, almost all kinds of order in condensed matter until about 1980 was in terms of some form of symmetry breaking. As you probably know, we can classify crystals, for example, by what rotational and translational symmetries they have. They have fewer than the vacuum, which is completely invariant under continuous rotations and translations. But symmetry breaking, aside from classifying crystals, you can classify all sorts of matter. Magnets are one that's kind of relevant to topological insulators and things like that, which are how I got into this field some years ago. But maybe the sort of universality that exists as a consequence of symmetry breaking, I want to introduce that as a way to think about topology, because topology gives you a different kind of universality that is even simpler in some ways. So the famous universality at second-order phase transitions, which is what made me want to be a condensed matter physicist, is just that if you take a system like water and forget about ice, just think about the boiling transition of water, there is a critical point where that goes away at high pressure and temperature, and the way it goes away is some power of the distance from the critical point, and that power is 0.3 something. People now know this to much higher accuracy because of conformal bootstrap, actually, theoretically. If I take a bar of iron and I heat it up, the magnetism goes away, and at least in our theoretical Ising model of a magnet, the way that the spontaneous magnetization goes away is again some power law. And of course the magic is that even though the magnet is very quantum mechanical and made of electrons and the fluid is pretty classical, the exponent is the same. So what happens in topological states is that effectively a response that you can measure is the same. You don't need to look at an exponent, you just look at what directly comes out of your experimental apparatus. And the beginning of the field was the discovery of the integer quantum Hall effect. Very briefly, when you get a new material, almost the first experiment you do, if it conducts at all, is apply a magnetic field, run a current, and measure the voltage that builds up because the current gets bent by the magnetic field. And if you convert that to a conductivity, what you see in some two-dimensional electron systems is that there are these plateaus. So in other words, at weak field, or in most materials, you see just a straight line dependence of transverse resistivity on magnetic field. But if you do this in the right two-dimensional systems, you see flat plateaus that are incredibly flat. On one of those, what you measure is an integer times e squared over h to about 1 part in a billion. And this is the property that was used to sort of redefine units recently. And this is I'll tell you where this comes from. It's not the original picture, which is due to Laughlin. It's a picture due to Thouless that was forgotten, or at least not widely used for a long time. But it's the picture that winds up being crucial for topological insulators and other recent discoveries. So 2 questions you might have. One is that, if I make a very good sample, I'll see additional plateaus at fractions, which are a very beautiful thing that happens, but I'm not going to talk about today. Pretty much everything I talk about today you can understand just in terms of electrons. They don't need to break up or form a big correlated state. And the second is there's another measurement you can do, an even older one. If you measure the AC Josephson effect, that lets you obtain the ratio E over H. So by 2 measurements on big chunks of solid, you can measure both E and H, the 1 particle charge and Planck's constant to incredibly high accuracy. So I'm eventually going to build up to optics, and let me maybe make one statement about how topology fits in with what we already knew about responses in condensed matter, or in physics in general. So in general, symmetry is a powerful tool to figure out what materials might allow a certain response. So for example, if you want optical responses, inversion breaking is required to get second harmonic generation, which means light comes in at omega and comes out at 2 omega. If you want to build a solar cell or something with a photocurrent under unpolarized light, that's a polar material. And then chiral materials will be the ones that are important for the effect I want to talk about. A chiral material you could think of as having like a left-handed or right-handed spiral to it. So symmetry still works in general, but topology sometimes gives you a magnitude that is very universal and independent of microscopic details, like that n times e squared over h. And it's also true that we've learned a bit more about symmetry in this era of topological phases. So as an example of that word topology that's actually very relevant to the way it's going to work in solids, suppose I take two-dimensional surfaces that live in three-dimensional space. And here's a famous, cute example of quantization in our language. If I take the curvature on one of these surfaces, let me define a Gaussian curvature as 1 over the product of the radii of curvature. And I want the sense of that, the sign, to be if both the directions are the same, like away from me or toward me, like on the sphere, that's positive Gaussian curvature. If one is toward me and one is away, that's negative Gaussian curvature. And the cylinder has 0 Gaussian curvature. So now the magic comes, this has units of 1 over area. If I integrate that over the area of a closed surface, let's do the sphere. So that's surface area 4 pi r squared. This is 1 over r squared, so I get 4 pi. But that's not only independent of the radius of the sphere. Even if I distort the sphere into an egg or a football or whatever, I'll still get 4 pi. But if I took the donut, the vada, the torus, whatever, the curvature on the outside cancels out the curvature on the inside, and overall, the total curvature is 0. And the Gauss-Bonnet theorem is just that the total curvature of a closed two-dimensional manifold is just given by the number of holes in sort of a quantized way. So we're now going to do something like that for solids. So for example, insulators tend to come in classes that are labeled by a topological invariant. And the topological invariant is a kind of integral of a curvature again. And the curvature is made out of the wave functions, where wave functions means just that if I go into a crystal, the wave functions are plane waves times something with the periodicity of the crystal. That's Bloch's theorem. So wave functions of this form, I'm going to use U, which is something about the electron wave function in the unit cell, to define my curvature. And then I need a surface to integrate that over, and the surface is just the Brillouin zone. So the geometric phase I want to talk about, and I'll talk about Berry and Pancharatnam in a second, is what's going to give us the curvature. So first, where this phase winds up being useful, it started off as a way to understand topological phases because it gave something quantized. That was the quantum Hall effect. And then where I got interested or got involved was topological phases that exist when you have a symmetry in the material. So for example, non-magnetic materials have time reversal invariance, and that lets you define a new kind of topology, which is not labeled by integers, it's labeled by even odd, like Z2 or parity invariance. And then these phases also wound up being useful to do electrical polarization and magnetoelectric effect and things like that. Basically quantities that are sometimes quantized but generally not, but always have a piece that comes from the geometric phase. And then the new stuff I will be talking about is about metals. So let me define some things. Let me do the continuous version first, although historically the discrete version, which I have on the next slide, of course, came first. So when I go into a solid, we have wave functions that depend on a parameter, namely momentum. And whenever you have wave functions that depend on a parameter, there's a beautiful sort of gauge structure that's very much like what you learn in electromagnetism. What I mean is, let me define this quantity, which I'm going to write like it's a vector potential, in terms of how some wave function evolves as a function of parameter in some high-dimensional parameter space. at least more than one-dimensional parameter space usually. So that object, I can integrate it, and at least by power counting, it might give me a phase. Why do I write the phase like this, and what does it govern are sort of the things I want to talk about. But maybe this is saying that the adiabatic theorem is only half of the story. Adiabatic theorem says that if you have a non-degenerate state and you change the Hamiltonian slowly, you remain in that state. But this is saying that there's some geometric information that we don't always teach. And then, of course, Berry was not the first person to talk about geometric phases. His paper was really a unification of ideas that had appeared elsewhere. Pancharatnam thinking about optics, Longway-Higgins thinking about molecules. And to explain how they're connected in sort of modern language, whenever we actually compute one of those Berry phases, even though we write it in terms of gauge fields and so on, the way we actually compute it is like what Pancharatnam did in terms of projection operators at discrete points. So as an example, I haven't said much about the Berry phase being well defined yet, but supposing that I wanted to calculate one of these phases, or e to the I phase, if I tried to discretize that, I would get a lot of overlaps between nearby points. And those overlaps I can kind of rearrange into projection operators. So basically there can be a geometric phase in the product of projection operators. And that's what was first realized by Pancharatnam when he was, I think, a student here. And one reason, there are basically a couple of reasons why we wind up using expressions like this to actually evaluate things. One is that the projection operator, if I can manage to work with that, it's explicitly gauge invariant in a way that the wave function is not. So the wave function has a U1 gauge invariance. You and I might disagree on the phase of the wave function, and we'd both be right. But we won't disagree on the projection operator because one of these gets, say, e to the I theta, and the other one gets e to the minus I theta. So the way that that gauge invariance doesn't become a problem and actually becomes almost a good thing as far as a guide for physics is that if I make that gauge transformation, I realize that the Berry connection, this vector potential, shifts by a gradient of the phase. And that gradient, well, that means that A itself at one point in parameter space isn't observable because we will disagree. But just like in electrodynamics, I can make gauge invariant objects. And the simplest one, which we now call the Berry curvature, is just the curl of A. And one area of some recent work, magnetoelectricity is governed by a sort of non-abelian version, like a UN instead of U1 gauge field, which just means if I've got multiple bands that all contribute, it's natural to define an object with band indices. All right, so what is this Berry curvature good for? Well, this is where Thouless came in. And Thouless actually wrote his paper at the same time as Berry was writing his paper. And what Thouless, Komoto, Denice, and Nightingale figured out was that if I define the Berry curvature in the Brillouin zone of a crystal, then the quantum Hall effect is governed by some integral of the Berry curvature. So the history is that Laughlin gave an explanation for the integer quantum Hall effect by inventing a sort of new kind of transport, pumping. But Thouless wanted to ask, if I just started from the Kubo formula, kind of our standard definition of conductivity, could I derive that something is special in the quantum Hall regime? And the answer is basically this formula, that there's an integer for every band. Every band in a crystal will have an integer, a Chern number or TKNN integer, and that integer is basically just the integral of f, maybe divided by 2 pi. That's what this reflects. And then if I want to know the quantum Hall effect of a material, I just sum up those magic integers. So if you like, a band in a solid has an integer associated with it that's like that topological invariant of total curvature of a 2-manifold. All of these vanish if I have time reversal symmetry. That's why the new topological insulators were kind of a big deal, because they're the first topological states that exist without requiring magnetic fields or magnetic materials, and also the first that exist in 3D. I'm not going to talk too much about those today because it's now, as much as I hate to believe it, it's almost 20 years old, and I wanted to talk about newer things. But I will talk a little bit about one example. So the lesson, as I mentioned, this is the same slide again, but just with these objects A and F, we can explain a lot of old puzzles about responses in solids and also ask some new questions. So as an example, here is this is mostly, I know there are people here doing all kinds of physics, like particle physics or quantum gravity or whatever. There's a sense in which the three-dimensional topological insulator and the band structure picture of that was something I worked on quite a lot around 2005, 2006, was sort of anticipated by particle physicists like Wilczek a long time earlier. They weren't thinking about solids, they were thinking about, at least not about bands and details, but they were thinking about just kind of symmetries and a particle called the axion. The axion field would couple to ordinary electricity and magnetism like this. They're still looking for the axion, by the way. It kind of went out of fashion for a while, but now it's back in fashion as a possible dark matter candidate. Anyway, what Wilczek showed basically, or maybe put in solid state terms at least, was that you should think of the coefficient of E dot B in a sense as an angle if I only have the bulk of a material. If I don't have any boundaries or anything, then you could think of it as an angle. E dot B is special compared to E cross B and other things, incidentally, because E dot B is a total derivative. It's almost like something you could move to the boundary if there was a boundary. So if you're willing to trust me, and I'll give you the condensed matter picture in a second of why this is like an angle, or at least some ways that that all works out, then if you have an angle that is odd under a symmetry, and here time reversal takes theta goes to minus theta, basically the point of Wilczek's paper, which was ahead of its time, was that if we impose time reversal invariance, maybe there are actually two kinds of insulators in our world. There's one kind with theta equal to 0 and one kind with theta equal to pi. And at the time, they didn't have any examples of theta equal to pi. But in hindsight, the 3D Z2 topological insulators are the theta equal to pi materials. And I'll try to connect that with sort of the standard definition of a topological insulator in the next slide or two. Because yeah, the band picture is that there are two kinds of three-dimensional insulators with time reversal symmetry. One kind will have an even number of Dirac-Cohn surface states, which could be 0, so that's the ordinary insulator. But another kind will have an odd number of Dirac-Cohns at the surface, which basically means even though it's an insulator, it always has a conducting surface, and that's what we call the topological insulator, Leon Balenz and I. So how is that picture of an insulator with a Dirac-Cohn surface state connected to the Wilczek picture of some kind of theta angle? Well, the way it all works out is that this bulk term, I said it was a total derivative. It's basically a total derivative of a surface Hall effect, basically a surface layer with a sigma xy. And then theta acts like a kind of offset where instead of getting an integer Hall effect on the top, I get some offset by a fractional part and an offset by a fractional part the other way on the bottom. And the way E dot B, if you're wondering how does that come from surface Hall effect, you could imagine applying a current, running a response current around the sample because of sigma xy, and that produces the B. So there's a kind of quantized magnetoelectric effect. And it turns out there's a famous experiment on graphene that indirectly proved the main fact that needs to be true for this to work. So when graphene was first discovered, people were really optimistic that it was made up of 4 Dirac cones, but they needed a measurement. And the measurement was that basically, if you measure the quantum Hall effect in graphene, you don't see 0, 1, 2, 3, 4. You see a strange pattern of integers. You see like -6, -2, 2, 6, 10, 14. And those are basically 4 times the half integers. So that's kind of a proof, if you like, that one Dirac cone would have a half integer Hall effect. At least an experimental proof. Of course, there are theoretical arguments, but those would be more tedious. So that's the kind of physical connection between the 3D topological insulator and the magnetoelectric effect. There's one deep kind of mathematical result that comes out of that in terms of these geometric phases, which is the star, that I'm not going to try to derive here, but I wanted to explain it briefly because it's an example of how if you find something beautiful in one area of physics, it will appear maybe in others. So I have this chair called Chern-Simons at Berkeley because Jim Simons, who passed away recently, was a student at Berkeley, or later worked with Chern, the great geometer, and they realized that there's a kind of form of gauge fields, we would say, called the Chern-Simons form, and that was possibly useful in other areas of physics. It's definitely useful in the quantum Hall effect, and it's even useful in three-dimensional solids because if I try to compute that theta angle from band structure, it is given by the Chern-Simons form, this complicated object of those Berry phase gauge fields. And if you're wondering, how can I see from this that theta is periodic? Well, a well-known fact about the Chern-Simons form is that if you can make large gauge transformations that are not contractible to the identity, and under one of those transformations, things shift by a quantized value, and it's just enough to shift theta by 2 pi. So everything kind of hangs together. So that's my most, I think, mathematical slide of the talk, if you're interested in field theories and Chern-Simons forms and things like that. So now I want to talk about, I think I'll skip this, but in order for that to work, you actually need to think about the non-abelian. Oh, yeah. Axion is? People have not yet found an axion. It is a particle that they're looking for. But in a solid, the basic idea is that an axion would be a field that couples to electromagnetism in a certain way. But if you go into a solid, you get terms that have the same structure even though there's no axion. So I don't know of any experimental evidence that we have axions, but in solids, this term still exists in the electromagnetic Lagrangian. Does that make sense?
It has no charge, speed, and mass. Any idea of axion?
I mean, for us, the axion, the axion candidate particle has some range of possible masses, which is where people are looking for. But for us, yeah, I don't really need even though Wilczek called this axion electrodynamics because this coupling is like the axion coupling, I don't actually need the axion particle for anything I'm doing. Okay. So it turns out that the simplest application of the geometric phase in solids is actually in metals. And it's a bit of a sad story where people like Tarplus and Luttinger knew that this term existed, but they couldn't convince people because they didn't know, I mean, people hadn't worked out its connection to the geometric phase. And this term, this is the one that's not in classic books like Ashcroft and Merman. I'll try to explain a little bit where it comes from, but this is the same F, that Berry curvature that I talked about before. And when you add this, it actually makes the equations of motion for a wave packet in a solid a lot more elegant, basically, because if I look at the force equation, you know, the Lorentz force has an E plus V cross B. It's got 2 terms. The old-fashioned equation for the velocity just has this group velocity, and as you know, if you go into a crystal, you modify the effective mass and so on. But now there's a second piece, which is kind of like a magnetic field in the Brillouin zone, and it comes from that Berry curvature again. And if you're wondering why is this term there and why had people sort of missed it, it's not there if you have both inversion and time reversal symmetry, which is many materials. However, in other materials, what can happen is that, let's say I've got 2 atoms in the Brillouin zone, like atom A and atom B in different places. Then maybe as you change the momentum, the orbital shifts from A to B. So that's like a motion inside the unit cell. So basically the fact that electrons have non-trivial structure within the unit cell in a crystal, which is that U wave function, that shows up in this term. And therefore it matters for a lot of things having to do with transport and optics and so on. But the open question, I mean, I'll tell you where people think this is important. It's actually important in like a bar of iron. But it doesn't give you anything quantized. And you might think it's hard to get anything quantized in a metal because you can always just change the Fermi surface by a bit and everything will change. But that's not quite correct. And if, yeah.
So what are the subscripts A and B, do you know?
Yeah, so these are just spatial coordinates, like, you know, X, Y, Z would be 1, 2, 3 for A. So if you want, it does have a structure a bit like a magnetic field. You could think of this as something like, okay, so this F with AB, you'll sometimes see it written instead as like a vector, and then this vector would be like F cross K dot. Yeah, sorry, I should have said people use 2 different notations for F in 3 dimensions. Sometimes you write it as a vector, and sometimes you write it as a two tensor, and the relationship is just the epsilon ijk. Thank you.
So it has some tensorial representation, sometimes in the literature.
That's right. Yeah. Yeah. So the way that connects to another quantity, which is the electrical polarization of an insulator, you can kind of understand, you know, why does F show up in the effective velocity? The polarization is just the loop integral of A. That's probably the simplest geometric phase quantity. That's the one computed by that product of projection operators, a la Pancharatnam. If you think about polarization changing in time in a crystal, that would be like dp by dt or dA by dt. dA by dt is like dA by dk times dk by dt, and that's basically this expression, because F is dA dk, and this is dk dt. So this is something like the total change of polarization, if I could define polarization in a metal. So there winds up being sort of a recipe for which quantities are likely to be Berry phases, and that's what this little cryptic comment at the bottom is about. But basically, low symmetry materials are the ones where geometric objects of various kinds need to be added to the standard theory of solids. So if you measure a bar of iron, or in general, a magnetic metal, this is about the different regimes of what controls the Hall effect. So Hall, around 1890, was measuring chunks of magnetic and non-magnetic metal. If you make a very clean metal, that's actually the simplest case, and it winds up being described by kind of scattering at the Fermi surface, normal theory of metals. If you make a very dirty metal, it's governed by localization. But there's a range of about 3 orders of magnitude, which is typical metals if you make them without great care. And then the largest part of the Hall effect is actually the same integral. This is called the intrinsic Hall effect. Even if it's not quantized, it still doesn't care about the details of scattering. It's just an integral over the Fermi sea of F again. So that's what Karplus and Luttinger were talking about and what people only understood much later. But it's very hard to do any rigorous calculation. You can see even by the time they get to figure 47 of this review, they're still at a speculative and schematic phase diagram, because it's hard to study the middle. You know, we're all good as theorists at the extremes, but the middle is harder. So I now want to come, this is the optical effect that in ordinary metals, it is a Berry phase quantity, but it's not quantized, and we were happy to figure it out because we thought it explained some experiments, but I wouldn't call it deep. It's very simple. It turns out that in the new materials, it does something a lot more surprising. So the effect, and I'll try to draw a semi-classical picture of it because that's fine in old materials, is called the circular photogalvanic effect or chiral photocurrent. Basically, you take a material, you shine circularly polarized light on it, and you sometimes find that right circularly polarized light makes a current, a photocurrent, go one way, and left circularly polarized light makes a current go the other way. So photogalvanic effect just means like photocurrent, light induces current. So imagine that we have a two-dimensional material whose ground state electron distribution is the black circle. And then the light comes, and the electric field of the light in semi-classics just kind of pushes the electron distribution a little bit away, and then it reaches a steady state. So if at low frequency, circularly polarized light means that the gray circle of where the electrons are will kind of rotate around the black circle. And you can believe that the ordinary velocity will average to 0 in that process. But if you have a low symmetry two-dimensional material, like some quantum wells, the anomalous velocity will not average to 0, and that's this photocurrent. So it's a direct way to measure the Berry phase in some of these two-dimensional materials. And the way we got interested, there were a lot of experiments over decades by someone in Regensburg named Ganichev, who had done this very carefully and had originally thought it had something to do with spin-orbit coupling because he saw it in materials with strong spin-orbit coupling. Then he was a very honest experimentalist. He did it in silicon, which doesn't really have spin-orbit coupling, and saw essentially the same strength of the effect. So it clearly had to come from something else, and it comes from this inversion symmetry breaking induced geometric phase. So now I come to the new materials that kind of made some big recent progress in condensed matter. So if you go back, oh, yeah.
So why did you say direct measurement of Berry phase in the previous slide?
Yeah, just it's a little bit, okay, I suppose it's a little bit more direct than measuring here the DC transport because you have an extra knob, which is frequency. So I wouldn't, yeah, direct, because the ordinary velocity doesn't contribute, I think ordinary scattering contributes less to this than to some other effects. I wouldn't say it's like a perfect measurement of the Berry phase, but I think it's better than DC transport. If that makes sense. The problem is you need a very intense terahertz source because it's quite a weak effect.
That's why it might change your system, right, when you try to calculate.
But I don't think, I think, I think that would be higher order, yeah, that would be higher order, I think, in the electric field. I think it's such a light-induced modification of the crystal. Yeah. So I think it's there, but it's relatively weak, yeah.
I was wondering, so this effect you said, this paper, that with circular polarized light, so in case orbital angular momentum carrying light interacting with metal, so should that be similar? Means there is light which can carry both orbital angular and the spin angular momentum.
Yeah, I think that would be interesting to study. I mean, the generalization of this is now called the nonlinear Hall effect, and it's like in a paper by Soderman and Fu. I think it's a good question, and I don't know the answer about whether there are some, generalizations of this to beams with orbital angular momentum. Someone might have thought about it, but I don't know the answer. So now go back to the early days of quantum mechanics, and so even before, like, graphene was predicted, I think, in 1946. Even before then, people had predicted sort of three-dimensional versions of graphene, and there are really two kinds, and they were discovered experimentally around 2013 to 2015. So the Dirac equation is, 4x4 matrix equation, or if we were going to try to make a condensed matter version of that, that would be like a 4-band semimetal with linear dispersion in 3 dimensions, and that was found in these materials. So soon after Dirac wrote down the Dirac equation, people realized that there are 2 different ways to make half of the Dirac equation, to break it down from 4x4 to 2x2. And those 2 different ways are kind of an active topic, both in condensed matter and particle a little bit now. So the 2 ways, one was figured out by Weil, and if you have massless particles, so unlike the electron, if you have a massless particle, then it turns out that you separate the 4x4 equation into like a right-handed piece and a left-handed piece. The idea is that for a massless particle, suppose it has positive helicity, so it's like spinning one way relative to its motion. Because it's massless, you can never go to a frame that is moving faster than the particle to flip its helicity. Basically, for a massive particle, you can flip helicity depending on what frame you're in, and that means that the 4 components get mixed. But for a massless particle, in general, left and right-handed will separate, and people thought for a long time that maybe the neutrino was a Weil fermion, but then people discovered that neutrinos have mass some time ago. So they're not in the standard model, but you can get basically massless Weil fermions in some materials. The most popular is tantalum arsenide, but now there are quite a few other examples. So a big question is, what are these good for? The other way to take half of the Dirac equation is to assume that the particle is its own antiparticle, and that's what Majorana did. So the neutrino may not be a Weil, but we hope that it's a Majorana. So the topological meaning of that was explained by a number of people. So that we didn't have in the 1930s, but basically, if you take one of these massless points, so a Weil point is somewhere where 2 bands come together, like in a 3-dimensional version of graphene, I can make a little sphere around that point, so that's a 2-dimensional manifold, and I can integrate the Berry curvature through that little sphere. And the total Berry curvature winds up being quantized. If you like, every Weil point is a monopole of Berry flux. It has an integer charge, which is like a monopole charge, and there's a theorem, the Nielsen-Ninomiya theorem, says that the total charge of all those points has to add up to 0 in a crystal. I'll give you a reason why there'd be a problem if that wasn't true. But that doesn't mean that they have to cancel out at the same energy. Like a Weil point turns into a Dirac point if I bring 2 Weil points together, and then they could gap. But one of them by itself is very stable. The way that they were first observed experimentally is an interesting prediction by this group of people. Ashwin Vishwanath is a native of Bangalore, so some of you may know him. The surface state of one of these Weil semimetals has, instead of a Fermi surface, instead of a closed loop, it has an open Fermi surface or a Fermi arc that kind of connects the projections of the Weil points. And this is a little bit of an odd picture because it, you should think of the bottom as real space and the top as the Brillouin zone, so momentum space. But basically the Fermi arc on top is closed only on the bottom of the sample. So both topological insulators and Weil semimetals are a way that you get a surface state that's kind of half of what you're used to. So anyway, that was seen in photo emission. That kind of led to the discovery of the materials. what I want to talk about is an optical effect that is sort of similar in spirit to this thing I mentioned about graphene, but more fundamental or more topological, even if not yet as precise in the lab, because it's, well, for interesting reasons. So the reason why there would be a problem if we could find a Weil semimetal that only had one Weil point is something called the chiral anomaly, that any particle physicists in the audience will know better than I do. Basically, if you had a charged Weil fermion, you know, if in my crystal it's made up of electrons, so there's a charge, and if I applied parallel electric and magnetic fields, anomaly in this case means that there's a problem with charge conservation. I would spontaneously create charges, which we don't think should be possible. This C is the charge of the Weil point, so it's good that total charge is 0. That means that applying E and B sort of pumps charge from a positive Weil point, say, to a negative Weil point. So the total charge is 0, and people have tried to find signatures of the chiral anomaly, and I personally don't think they've been entirely convincing in solids. What I want to talk about is something else that's also quadratic in the fields. And there's a way by power counting you could have guessed that something interesting would happen in 3D with a pair of fields. And that is, if I were to write that two-dimensional quantum Hall effect and forget about the transverse indices and things like that, basically it's apply an electric field and I generate a two-dimensional current density. So what could happen if I've got two fields, like E and E or E times B? Well, by power counting, it turns out I need to add 1 power of inverse length, which takes me from 2D to 3D, and 1 power of inverse time. If I had E and B, this would be dN dt, and that would be my chiral anomaly charge injection. That doesn't seem very physical, but current injection is very common, like in a solar cell or something like that. You shine light on the material and you induce a current density. So this says that at least you might hope that there could be a quantized rate of current injection in some three-dimensional materials. And it turns out that that's what happens, we believe, in Weil semimetals. I think that's the most interesting thing so far, maybe, that Weil semimetals do. So I'm going to skip about the history of linear effects in Weil semimetals, even though it took us and others a long time to convince ourselves that I don't think there's any really interesting linear optical effect in Weil semimetals. You have to go to nonlinear optics to see that they're different from ordinary metals. But it was already known that they were interesting from the point of view of nonlinear optics. So let me tell you something that is an experimental observation that I don't fully understand in any deep way, but it's one way that these Weil semimetals might actually be useful. So it turns out that they're about the strongest nonlinear optical materials that we've found in the following sense. They have this second harmonic generation. You send in light and you get out light at 2 omega. And that signal is so strong that my experimental colleague, Joe Orenstein, who saw this, he said it's the only experiment in his life where the first time he measured it, it was much stronger than he was expecting, and even so strong that he had to turn down his amplifier, basically. And if you want to understand what I mean, this quantity here is sort of like the dimensionless strength of second harmonic generation. And you can see that at just some randomly chosen frequency set by the laser, it's already about 10 times larger than the standard materials, such as barium titanate, used for nonlinear optics. The one reason why you shouldn't start a company or something is because this is a semi-metal, it's kind of lossy. You know, there's low energy degrees of freedom, you can damp and dissipate. But if you just care about strength of the effect in a short distance, say, this is very good. What I'm going to talk about is a different sort of Weil semi-metal that has an effect that is not quite as strong, but is quantized and more interesting. I think this just means that tantalum arsenide is very polar. It strongly breaks inversion. We did do a little bit more work. So now coming back to this effect, the basic story is going to be that same circular photogalvanic effect that we studied in 2010 semi-classically. You have to do it quantum mechanically in Weil semimetals, and I'll sort of draw a picture of why in a second. And when you do that, you find this quantization. So at least in the in the independent electron approximation, it's quantized, and I have one slide on why interaction corrections are moderately large, I think larger than in graphene. So here's the effect and why you don't actually need to get the Fermi level to the Weil point. So the Weil point are these crossings. The Fermi level is here. So this, in ordinary transport, this would look like a fairly ordinary metal. It's got a finite size Fermi surface and so on. But if I now think about optical transitions, you know, this optical transition is allowed and it crosses the Val point, which means, you know, something is going on that's strongly changing the Fermi surface. I wouldn't, oh, yeah.
Can we understand the setup little mechanics what you are saying? We have a 2D materials and you are shining light for this one?
No, for this one, it's going to be a three-dimensional material, and I do have a picture of the experimental setup in a second. But for now, let me just think about the band structure of the material. So yeah, the circular photogalvanic effect experiments, the old ones by Ganichev, were on two-dimensional materials, and it was a current in the plane. This is going to be a three-dimensional material, and effectively, the current is going to run kind of from the surface into the sample. So what you're actually going to detect is the radiation from that little burst of current. But I'll say more about that in a second. So yeah, this is really an intrinsically three-dimensional effect, I think. I don't think there's any way to do this in 2D. Anyway, the point is that I can find frequencies where, at least if I can get a large enough splitting between the positive and negative Val points, and here these are what I mentioned about Berry flux monopoles, positive and negative, then optical transitions across this one, they don't happen because the final state is already occupied. That's Pauli blocking. They happen here though, and it turns out that the strength is about 100 times larger than in the old experiments. In other words, a Val point produces a very large and quantized rate of current injection. Basically, the rate, you know, again, difference between right circular and left circular is fundamental constants times the intensity of the light times the charge of the Val point. And I'll come to the experiment in a,
How is it different from like Faraday rotation? Because Faraday rotation is also because of left and right circular polarization.
yeah, Faraday rotation is linear. And actually, the slides that I kind of skipped over, this is all about Faraday rotation. Yeah, and my belief is that Faraday rotation in a Val semimetal, I mean, you will get some rotational angle, but it's not quantized. So this is a nonlinear optical effect. You know, Faraday is linear in E, and current injection is 2 powers of E. So in other words, like what appears here is the intensity, not the electric field, so E squared. So, but yeah, it is, I mean, I would say Faraday rotation, you can see it even with linearly polarized. I mean, you put in linearly polarized light and the plane of polarization rotates. So here it's more like right minus left, and it's quadratic. So people had thought about photocurrents before. Maybe the most important enabler of the experiment was these two papers. So Zahid Hassan at Princeton found a material that was much better for this than the material we had kind of been thinking about. Rhodium silicide is a Val semimetal with a big gap between positive and negative charges, which means there's a range of frequencies you can work over. That gap is about 0.7 electron volts, and that was explained here in some other, you know, detailed predictions about how this would work in the material. Rhodium silicide also has like Val charge of 4, so that's an extra strength of the effect. So what I mean by that gap or difference between Val energies being important, if you think about what should happen, let's say that this energy of the upper Val point is 0.7 eV from this lower Val point. What will happen then is you'll be dominated by only one of them at low frequency, but eventually you'll hit a frequency where, you know, if I increase the frequency a bit, I would get transitions from down here to up there. I would start to get transitions that were allowed across the other Val point. So the main qualitative prediction is that Val semimetals should have a very unusual response if you measure it this way. You should find a strong effect until the splitting, which is about 0.7 EV, and then it should suddenly turn off. And maybe these are some details of other ways to understand the quantization. You can get it from Fermi's golden rule done.
The previous slide, Cn is the charge. What is that Cn?
That's right, Cn is the charge of the Val point. Yeah. I mean, maybe the one thing to say about how to relate this to ordinary calculations you could do is it's a little bit like what Thouless did with the quantum Hall effect, where you start with initial and final states, and you might say, well, nowhere in the initial and final states does the Val point appear, because that's somewhere in the middle, so what's going on? Well, the answer is that the initial and final states, they know that there's the Val point in the middle because I can't open up a gap. It's sort of topologically stable, so something about the relationship between the upper and lower states is non-trivial, and indeed, by doing some mathematics, you can transform it into the Val charge times E cubed over H squared, like I said, but the math I will skip. it's probably worth saying that what really is quantized is this trace of 3 nonlinear conductivities. So now we come to the measurement. So this is all optical, and it uses basically a laser high frequency pulse coming in. That high frequency pulse comes in, and it drives a little bit of current into the bulk, and that current would be a DC current if this pulse lasted forever. This pulse isn't very long, so the burst of current lasts about a picosecond. In other words, rather than the frequency of these...
And the pulse is linearly polarized too.
No, we want to measure, again, the difference between right circular and left circular.
The pulse, original pulse is linear polarized, or that all? What type of pulse?
So there's a laser that comes in and then some radiation that comes out. And the laser that comes in is circularly polarized pulse. Yeah. So yeah, basically, the reason why linear wouldn't actually do anything is that right circular drives it one way, left circular drives it the other way. Linear is like adding right and left circular, so linear will cancel out.
But is there a different direction, you will get different?
You can get other linear effects if you wanted, but here, I mean, the way to think about what's going on, you're creating a burst of current, and that is radiating basically perpendicular to it like any other burst of current would. So that's the observable. And that the strength of that current you measure through the terahertz radiation. So it produces radiation at a much lower frequency. So the light that comes in is at a frequency of like, typical laser inverse femtoseconds, say. Light that comes out is terahertz, much lower frequency. But you can measure that, and it's difficult to get the magnitude, but you can at least get the frequency dependence quite easily. There are later measurements by a group at Penn claiming to get the magnitude. And yeah, again, the main prediction to look for is there should be something like a high signal that falls off rapidly once the frequency goes above about 0.7 eV. And this is from 2020. And the reason why I'm talking about it is, of course, that it sort of works. The laser can't go to very low frequencies, but there's at least a strong signal. This is not the way photocurrents usually work. They don't usually have such sharp signatures. But anyway, there's a large signal that falls off right where it's supposed to fall off if you're getting to the frequency where the left and right val points cancel each other out. The magnitude, let me now explain why, just in closing, the magnitude I don't think can be as well quantized as in graphene, because as far as I can tell, that holding graphene up to the light is only as good as it is because of luck. What I mean by luck is that you can go ahead and compute corrections, and they are non-zero. They're of order up to 50% or so. It depends on frequency. And it's in graphene, there are also corrections, but with a lot of work, people summed up all the different corrections in graphene, and they managed to understand why it's small. Because if you're wondering why you might expect it to be large, the correction should in general be of order fine structure constant in the graphene. In other words, using the graphene velocity instead of the light velocity, and that would be of order 1. Instead, the correction in graphene winds up being 1% because of the magic. The magic is that the coefficient that you calculate after a lot of diagrams is 19 minus 6 pi divided by 12. And if you think about 19 minus 6 pi, that's kind of small. And you divide it by 12, and it winds up being about 1%. So no one, as far as I can tell, can figure out, why did this coefficient have to be 1%? That's strange, but it's something that you would, in other words, you would have expected in graphene that the quantization would be, say, instead of 2.3%, it would be anywhere between 1% and 3% or whatever. But graphene, many things work out better than you would have guessed. And then I just one last slide about where the field is going. This is actually something with linear pumping, but one power of the lasers that people now have that is motivating and should motivate theory is you can use them to break symmetries and drive materials into new states and so on and see new effects. And this is just one example of that field is if you start with a Dirac semimetal, you can turn it into a Weil semimetal by either running a current or using a laser to change the symmetries. So I think with that, I'll just wrap up, but maybe to explain why, even if I don't think this is going to be perfectly quantized, I like it because we can add it to our table of effects. We have linear in E effects like Josephson frequency and inverse flux quantization. We have quadratic in E effects, quantum Hall, graphene optical transmission, and so on. And now in nonlinear properties, we have an E cubed over H squared effect. And if you remember that kind of power counting argument, it seems like to get higher powers, we'll have to get more and more complicated experiments involving either higher dimensions or more derivatives. So I don't have any idea for an e to the fourth effect that is practical to measure. But on the bright side, it seems like we have these new materials, these Val semimetals. They're a fine example of how geometric gauge fields in crystals are real and predict things. And that's an idea, of course, that began here. There are two kinds of nonlinear optical effects, I guess, that are interesting in vowels. One is just that they're very strong and potentially useful, and this kind of led to the development of new sorts of nonlinear optical sum rules that are kind of interesting on the material side. And then on the more fundamental or topological side, rhodium silicide and also cadmium silicide and maybe some other materials people have studied seem to show some kind of nonlinear quantized effect. So with that, thanks a lot for the questions during the talk. I'm happy to have more, and thank you for your attention.
Yes, something to that guys, a well-known features of wild Harman is the chiral anomaly. Would you be kind enough to come to this slides again?
What was the last part again? Sorry.
That is this, hello, it's not working. Hello. Hello. It's working? Hello. Yes. Features of wild Harman is a chiral anomaly. Kindly come to that slides. Okay, something to say, why you use this term anomaly here? Suppose there is no anomaly, simple chiral symmetry, then how this calculation and result will be differ?
Yeah, so we need to break chiral symmetry for a non-zero effect. But in general, if I don't have the vowel point, so I don't think our effect is precisely connected to the chiral anomaly. But I do think that if you don't have a vowel point, you won't get the quantization and the effect will be quite weak. And I base that on the kind of semi-classical calculation that basically, if you like, we've calculated this circular photogalvanic effect in two limits. If I just have an ordinary metal and the Fermi surface is not changing very much, basically, okay, what you could ask, what's special about the vowel point? If I have a normal Fermi surface and it's not changing very much, then we can usually calculate things semi-classically, and then you get a very weak effect and it's not quantized. In the vowel case, the Fermi surface is changing strongly and you have to do the full quantum calculation, and that gives you this very large quantized effect. So I think in general, a chiral metal, maybe an example is selenium. I have a picture somewhere. At least I guess I have a picture of quartz. If I took a chiral metal, it will have this effect, but it'll be much weaker. It'll be about 100 times weaker because it's in that semi-classical regime. So at the vowel point is much more quantum mechanical. But I don't really use in fact, I don't think we have a very good measurement of the chiral anomaly of vowel points yet. I think it exists, but it gets balanced out between the positive and negative points. So there are a lot of papers talking about chiral anomaly being observed in vowel semimetals, but I don't really think they're very convincing.
Okay, thank you very much.
So towards the latter part of the talk, one thing I didn't quite understand, you said they need a 3D material, so the current has to be perpendicular to the surface. Why is it that actually?
Yeah, so if I want to get the quantization, so something I didn't quite say is what are the polarization and current directions in this formula?
Yeah.
And the answer is down here. The quantity that, basically if I want to get the magic Chern number quantization, the meaning of these tensors, it's like I've got 2 powers of electric field and 1 power of current. So I've got like, EX, EY, JZ. And I need to kind of combine them together to get the quantization, and then that depends a bit on, field directions and material directions and so on. But for the geometry in this particular material, that means that it works. You do expect to get the quantized value for this particular direction of fields and current. But basically, if I only looked at one component, it wouldn't be quantized quite the same way unless I had some extra symmetry. So yeah, if you're in a high symmetry crystal, then these are not really independent of each other.
Okay.
I think it's, there are better probes of Chern number in other systems, like the integer quantum Hall effect is the best probe of Chern number probably, but I would say that this experiment, at least this frequency dependence, is saying that yes, you had a strong source of the effect that got canceled out once I started getting transitions across the other source. Because they can't measure the magnitude, you could say they can't see the quantization and they can't see the Chern number as an integer, but they can at least say that there are two special objects in the Brillouin zone.
Okay, so you are saying Chern number cannot be detected. Is it 1 or 4? You can't detect.
I think that not in the experiment I showed. There's some nice work by Liang Wu at Penn that is trying to get the magnitude, but I don't think I don't think this is a sufficiently accurate experiment to nail down that the Chern number is an integer. That's correct.
Thank you.
So, correct me if I'm wrong, but you don't need completely symmetric crystals, right? You need, how do you quantify that? And in particular, so the fact that you don't have full symmetry or some amount of symmetry is broken, I mean, not the discrete symmetry, of course, breaks the continuum symmetry, but you want further breaking of symmetry. So I guess a question is random structures, for example, I mean, to the extreme is an amorphous solid, but also things like quasicrystals. Are they things that could also be potential things that you would look at? I mean, where is the role of that breaking of symmetry? I'm curious about that.
So yeah, the degree of the breaking of symmetry shows up in that, for example, if I look at, so tantalum arsenide breaks inversion, but it isn't chiral. If it only very weakly broke inversion, then we would expect the nonlinear optical effects that depend on inversion symmetry breaking to be quite weak, but instead they're quite strong. So you could sort of take that as a measure of how far are you from inversion symmetry. For the rhodium silicide, that one is chiral. And again, basically if it was not chiral, then the positive and negative points would be at the same energy. That's maybe not obvious, but the chiral symmetry would take me from a positive point to a negative point at the same energy. So the fact that these are split by a fairly large energy, 0.7 eV, is a sign that it's strongly chiral. So this idea of amorphous materials or even quasicrystals, people haven't studied as much for metallic behavior, but there has been a lot of work, even some experimental work on can you have an amorphous topological insulator? Actually, Francis Hellman and Alessandra Lanzara are two of the people who worked on this. You can make amorphous bismuth selenide or amorphous bismuth telluride and measure the surface state, and it looks a lot like the crystalline surface state. It has that sort of Dirac cone, even though momentum is not very well defined. That was like a Nature Materials paper in the last year or two. And we recently tried to say something about amorphous topological states. There it's a little bit easier because you have a gap and that can kind of protect things maybe. Like you might think that if I had a topological insulator of some kind, if there was a path to make it amorphous without any non-trivial states moving through the Fermi level, you might expect some properties to remain the same. And that's kind of the spirit of what's been done. I think for metals, there's not as much protection, and I don't know a lot. I mean, I know there are amorphous metals, but I would expect that effects like this are probably quite weak in amorphous metals, because as you say, there might be some restoration of symmetry, but I haven't seen any work on it. Can you say it again?
So in amorphous solids, like you told that there are seen these quantization things. So like, can we prove this theoretically if there is still doesn't have these symmetries, like translational symmetries?
Yeah, you can. I would say theoretically, people had worked out how to define topology without a crystal. There's something called the tenfold way, which is suppose I had, let's assume non-interacting fermions. Interactions are harder. Non-interacting fermions in some kind of random potential, and the only symmetries are not the ones that involve translations. So for example, time reversal, I could still have time reversal or time reversal breaking or whatever. So it turns out that there are two kinds of symmetries we mostly study that don't involve translations. One is time reversal, and the other is something that happens in superconductors. In some other cases, people call it a particle hole symmetry or chiral symmetry or whatever. And for each of those, you have three possibilities. And if you combine it all together, you wind up with 10 symmetry classes. And a beautiful result due to Kitaev is that in every dimension, there are 5 of those 10 classes that have some kind of non-trivial topology. So it's a way to kind of unify integer quantum Hall effect and topological insulators and various other things. So that makes me think that, yeah, we sort of knew that there could be a topological system that would have a surface state, but maybe the surprise is that the surface state doesn't just look like a totally random but still conducting thing. It actually looks like a Dirac cone. That I think you wouldn't have guessed, maybe. But yeah, there are ways to define topology even without translation invariance, but it would take me a few minutes on the board to kind of explain how that works. Yeah.
Thank you, sir.
Now this experimental setup you showed where you put this circular, yeah, that's so is it that only one kind of circularly polarized light can go in, or if you put the reverse, it works with both kind of circularly
It
polarized?
basically works in both polarized. I mean, you should think of the light does penetrate some depth into the crystal.
Okay.
But yeah, you can do it with either right or left circular polarized light, basically, yeah.
Okay, so, I mean, it doesn't like, the underlying crystal has both chirality in some sense.
Yeah, or maybe a way to put it is you don't, I would say that, yeah, the underlying crystal has one chirality, and that determines which one is positive or negative. But even if I just take like one, this is sort of the result for one vowel point. Mm-hmm. So in other words, one vowel point has a vowel charge, which you kind of think like a chirality. But when I measure that, the light chirality, or circular polarization, still matters. So in other words, yeah, I would say the material has a fixed chirality, but the consequence, you know, if I were to take suppose you had one sample that was chiral one way and another sample that was chiral the other way, then the effect would basically flip because the positive and negative points would flip positive and negative over relative to the Fermi surface.
So you're saying that even if I, like, for example, instead of right circular, if I put a left circular,
You'll find that
I'll get the same, I'll see the same behavior in the...
You'll see the same magnitude of the current, but in the opposite direction.
Opposite direction,
Yeah.
okay.
Aside from, you know, minor, probably surface-dependent details or something, but
Okay.
yeah, the interesting effect is the same.
Okay.
Will we accept any more question?
Sure.
Will we accept any more question?
Up to the chair, but I'm happy, yeah.
Hello, something to say from my common sense. I don't know whether I am correct or wrong. That is for the non-local order parameter, that is the topological phases of matter. Suppose I have the local order parameter, like the magnetism, superconductivity, or the Ohm's law type of transport Hubo formula. I think I can also use the very phase and geometry concept, because it's parametrically I am pumping the system by entering the adiabaticity. Am I correct or wrong?
You could well have effects in which the geometric phase appears, but they wouldn't be quantized. I mean, I think the special thing here is you have effects where, because of the mathematics of integrating, you know, this form, like maybe I would put it as in a normal metal, you will get the Hall effect. You know, in a magnetic metal, which has ordinary symmetry breaking and Landau-Ginzburg order parameter, you will get a sigma xy, and it will have a contribution from the Berry curvature. But only in the topological state is the contribution e squared over h, you know, fixed to some topological value. So yeah, if you want, I kind of think that wave function geometry and geometric phases are there in every material. Like, for example, electric polarization is a very simple observable in any inversion breaking material. It doesn't care if it's topological or not, and it's always a geometric phase. But for the quantization, that's what you need the topological phases for.
Okay, so if there are no more questions, let's thank the speaker for a very nice talk. Okay, so I also want to give something.
I see. Thank you very much. At least I know that something like this happens if you could put it in an optical lattice and make it like, yeah, I mean, there are some observations of Berry phase effects for atoms moving in an optical lattice, and you could try to see something like this there. It may not be the easiest thing. I mean, the one I worked on that I know about a bit, I have an atomic physics colleague at Berkeley named Dan Stamperkern, who does kind of neutral atom physics. And we had a paper on seeing Berry phases kind of near like a Dirac point in his version of graphene. So that was, I think, a science paper from the last year or two. So that was one, meaning sort of like a honeycomb lattice of laser beams, yeah. That's right, they make the experiment that they can kind of move the atoms through the Brillouin zone. I can see if I can find it quickly, but
Hello.
that's at least one
Hello,
sort of
check.
thing.
1, 2, 3. Hello.